Gravity is a force. Everybody knows that. You drop a pencil, it falls. An apple comes loose from a branch, it falls. The moon circles the earth because the earth is pulling on it. The sun holds the planets in line because the sun is pulling on them. This is what Newton taught us, and Newton was right about so many things that we named units after him. We put him in every textbook. We built whole branches of engineering on his shoulders. And he was wrong. Not wrong the way a sloppy man is wrong. Newton was one of the finest minds the human race ever produced. He was wrong the way a fellow standing at the edge of a pond is wrong when he looks at the reflection of a bird and thinks he's seeing the bird. He is looking at something real. He is describing it beautifully. But the thing he is describing is not the thing itself. It is a shadow on the water. I want to tell you today what the actual thing is. I have to warn you up front. What I am about to tell you about gravity is, in my opinion, the single most counterintuitive idea in the whole of physics. Stranger than the quantum business. Stranger than the relativity of time. When Einstein first worked it out, he called it the happiest thought of his life. When I first tried to wrap my head around it as a young man, I thought somebody had made a mistake. It turned out the person making the mistake was me. I was thinking about gravity the way Newton taught me to, and that way, beautiful as it is not how nature actually does the business. Before I show you what gravity really is, let me sell you Newton's version. Because Newton's picture was so clean, so successful, so spectacularly confirmed, that to throw it overboard, you first have to see why anybody would ever have believed it. Newton, in the late 1600s, sitting in his garden, watches an apple fall. That is the story. Whether it is true in the details does not much matter. What matters is what he did next. He looked up at the moon and asked a question nobody had quite asked before. Is the moon falling too? The answer that made Newton, is that he said yes. The moon is falling. It is falling the way the apple is falling. The only difference is that the moon is moving sideways fast enough that by the time it falls, the earth has curved away beneath it. So it keeps falling and never hits. An apple pitched with enormous sideways speed would do the same thing. Become a moon. Circle forever. This was a stunning leap. Before Newton, the heavens and the earth were two different kingdoms. Up there, the perfect spheres moved in their celestial dance. Down here, things got dirty and fell. Newton erased the line. He said the same law runs both worlds. An apple and a moon obey the same rule. There is no up there and down here. There is just matter, doing what matter does. The rule he wrote down was simple and beautiful. Any two lumps of stuff pull on each other. The strength of the pull depends on how much stuff there is in each lump, and it falls off with the square of the distance between them. Double the distance, 1/4 the pull. Triple it, 1/9. You could write this rule on a napkin. You could teach it to a bright child. And with that rule, you could predict, with astonishing accuracy, how the planets moved, how the tides rose and fell, how a cannonball arced through the air, how Jupiter's moons swung around Jupiter. People used Newton's law to predict the existence of a planet they had never seen. This was around the 1840s. Somebody noticed that Uranus was not behaving quite right in its orbit. Something was tugging on it. A fellow sat down with Newton's equations and calculated where that tugging thing must be. They pointed a telescope at that spot in the sky, and there was Neptune, just sitting there, waiting to be found. I mean, what a triumph. You use mathematics on a piece of paper to predict the location of a world, and the world is exactly where the mathematics says. At that point, you might say the case is closed. Gravity is a force. It reaches across empty space. It grabs objects and pulls them. It has a beautiful, simple law. The universe is a clockwork, and Newton has shown us the gears. For about 250 years, that is what physics said. That is what every school taught. That is what every engineer, every astronomer, every sensible person believed. I want you to feel the weight of that belief. This was not a guess. This was the most spectacularly confirmed theory in the history of science. Thousands of predictions, all of them correct. A law so good it felt like a law of logic itself. So when I tell you Newton was wrong, you should be suspicious. You should say, Feynman, wait a minute, how can a theory that accurate be wrong? And that is exactly the right question to ask. The answer is, his theory was not wrong in what it predicted. Most of the time. It was wrong in what it said was happening. Those are two different things. Let me tell you a story about that difference. Suppose you live in a house and every morning at 6 o'clock you hear a rooster crow, and then the sun comes up. Every single morning. Without fail. For 50 years, you could write a law. Rooster crow causes sunrise. Your predictions would be perfect. Every morning, the rooster crows and the sun follows. If somebody said, the rooster crowing does not actually cause the sunrise, you would say, prove it. My theory has never failed. Not once. But of course, the rooster is not causing the sunrise. The rooster and the sunrise are both effects of something deeper. The earth turns. When it has turned far enough, a bit of dawn light hits the rooster's eye and wakes him up, and he crows. A little later, from your window, the sun appears. Your rooster law is a lovely description. It predicts everything correctly, but it has the cause backwards. You have mistaken a side effect for the thing itself. Newton's gravity, in a deep sense, is the rooster law. It describes what happens. A planet orbits as if pulled by an invisible rope from the sun. An apple falls as if pulled by an invisible rope from the earth. The math of the rope is gorgeous and it works. But there is no rope. There has never been a rope. Nothing is reaching across space. Nothing is pulling. What is actually happening is stranger than anyone imagined. Let me show you the first crack. A small crack, tucked away in Newton's equations that nobody could explain, and that, if you stared at it long enough, would eventually break the whole picture. In Newton's law, mass appears twice, and it appears for two completely different reasons. Nobody could ever figure out why those two reasons gave exactly the same number. Here is what I mean. There is one kind of mass that measures how hard something is to shove around. Push a bicycle and it scoots. Push a truck with the same effort and it barely budges. The truck has more of what we call inertial mass. Inertial mass is the laziness of an object, its resistance to being accelerated. Then there is another kind of mass which measures how strongly gravity grabs an object. The earth pulls hard on a truck and pulls less hard on a bicycle. The number that measures how strongly gravity pulls on a thing we call gravitational mass. You would think these two things have nothing to do with each other. The laziness of an object and the grabbiness of gravity on that object. One is about pushing, the other is about being pulled. Totally different concepts. But here is the peculiar thing. Every experiment anybody has ever done says the two are exactly equal. From Galileo dropping things off the Leaning Tower, right through experiments that can measure to better than 1 part in a trillion, a truck's laziness and a truck's grabbiness, to the last decimal anybody can measure, are identical. Not approximately. Not close. Identical. Why? Newton had no answer. His law used mass here and the same mass there, and it worked. So he used it. When people asked him why, he essentially said, I do not frame hypotheses. Meaning, the math fits, leave me alone. For 2 centuries, this was just a strange coincidence nobody could explain. A quiet mystery, sitting in plain sight, inside the most successful theory in physics. Then, in the year 1907, a young man named Einstein, working as a patent clerk in Bern, had an idea about that coincidence. He imagined a man falling off a roof. Picture it with me. A house painter, up on a ladder, loses his footing. The ladder slips. He is falling. For 1 or 2 seconds before he hits the ground, what does he feel? Most people would say terror. But that is not what Einstein was asking. He was asking about the physics. What does a falling man feel in his body during the fall? He feels nothing. He is weightless. If he has a hammer in his hand, the hammer falls with him at exactly the same rate. So from his point of view, the hammer just hovers beside him. If he lets go of it, the hammer does not float away. It stays put. If he is holding a glass of water, the water does not slosh out. It sits inside the glass, as if the glass were drifting in empty space. During the fall, there is no up, no down, no weight, no pull. The painter is, for those few seconds, floating in complete freedom, the same way a person drifting in deep space, far from any star, would float. Einstein said this was the happiest thought of his life. He said he had been sitting at his desk at the patent office, daydreaming about this situation, and the idea hit him so hard he practically jumped out of his chair. Because in that falling painter he saw the key to everything. He saw that a man in free fall, who is supposedly being pulled downward with enormous force, feels no force at all. He asked a dangerous question. If the man feels no force, how do we know there is a force? The answer our senses normally give us, that gravity is a pull, comes from standing on the ground. Right now, as I speak, I feel my weight. I feel the floor pushing up on my feet. And my whole life, I have interpreted that feeling as gravity pulling me down and the floor stopping me. That is what Newton would say. But there is another way to read the sensation. Maybe the floor is not stopping me from falling. Maybe the floor is pushing me, and that push is the only thing I am actually feeling. Maybe if I just got out of the floor's way, I would feel no pull at all. Because there is no pull. And if I really fall, that is exactly what happens. The force vanishes. You have never felt a pure experience of gravity in your life. Not once. What you have felt is the floor. What you have felt is the chair. What you have felt is the shoe pressing into the ground. In every case, you have been feeling a surface that is in your way. Take the surface away, and the sensation goes with it. This is a completely different picture of what is happening. Let me push it further. Einstein imagined a second situation, even more powerful. Put a man in a sealed elevator, no windows. The elevator is in empty space, far from any planet, nothing around. Both the man and the elevator are just drifting. The man is floating inside, because there is nothing to pull him anywhere. Now some engineer attaches a cable to the top of the elevator and starts yanking, pulls the elevator upward at a steady acceleration. Inside, the man, who cannot see out, suddenly feels his feet pressed against the floor. He feels weight. If he drops his keys, they do not hover. They fall to the floor, gaining speed as they go. If you asked him what was happening, he would say, "Somebody turned on gravity. A planet must have appeared below me. Things are falling. I can feel my weight. But there is no planet. There is no gravity. The floor is just rushing upward to meet everything inside the elevator that is not bolted down." This is the kicker that changed physics. Einstein said there is no experiment the man can do inside that elevator to tell the difference. He can drop things. He can throw them. He can set up pendulums. He can do chemistry. Every single experiment that gravity would do, acceleration also does, and gives the exact same result. The laziness of objects and the grabbiness of gravity are equal to each other, because gravity and acceleration are, for a person inside a closed box, the same thing. Einstein called this the equivalence principle. He decided to take it seriously. If gravity and acceleration cannot be distinguished, maybe they are not just similar. Maybe they are, at the deepest level, the very same thing. That is a bold leap, a dangerous leap. Because if you take it seriously, things start to break. Let me show you one. Shine a flashlight horizontally across the inside of that accelerating elevator. The beam leaves one wall, traveling in a straight line. But while the beam is in flight, the elevator is accelerating upward. By the time the beam reaches the opposite wall has moved up relative to where the beam started. The beam hits the far wall a little lower than where it began. From the passenger's point of view, the light beam curved. If acceleration and gravity are the same, then light must also curve in gravity. A light beam skimming past a heavy object should bend. Its path should be pulled off a straight line. But wait, light has no mass in the old Newtonian sense. How is Newton's force supposed to grab it? Newton's law says the force depends on mass. No mass, no force. Light should sail through a gravitational field in a perfectly straight line, ignoring every planet and star it passes. Newton and the equivalence principle cannot both be right. Einstein went and calculated. He predicted that starlight passing near the sun would be bent by a specific, tiny amount. Not a huge bend, a small one. But enough to measure if you could see stars right next to the sun, which you can only do during a total eclipse. In the year 1919, during an eclipse, a British expedition went and looked. They photographed the stars near the darkened sun. They compared the positions of those stars to where they appeared on normal nights when the sun was elsewhere. The stars had shifted, exactly the way Einstein said they would. Light had bent, not because gravity grabbed it with a Newtonian force, because something else entirely was going on. 2.5 centuries of Newtonian victory ended in a single afternoon's photographs. And there was another piece of evidence, too. An older piece that Newton's law had never been able to quite handle. The planet Mercury. Mercury's orbit is not a perfect closed ellipse. It precesses, it wobbles. Each time Mercury goes around the sun, the whole ellipse rotates slightly. Most of the wobble is explained by Newton, because the other planets also tug on Mercury. But there was a tiny leftover, a little bit of wobble, about 43 arcseconds per century, that Newton's law could not account for, no matter how carefully astronomers measured. They added hypothetical invisible planets near the sun. They tinkered with the inverse square law. Nothing worked. When Einstein finally wrote down his new theory of gravity in the year 1915 and sat down to compute Mercury's orbit, his equations predicted that extra wobble. Exactly. 43 arcseconds per century. Einstein later said that when he saw the answer come out right, he got heart palpitations. He knew, in that moment, that nature had told him something true. All right, here is where I have to ask you to be patient, because the real picture is strange, and I want you to see it clearly. Forget Newton for a moment. Forget the invisible ropes. Forget the pulling. Imagine instead that space and time are not a fixed stage on which things happen. Imagine that space and time can themselves be bent, stretched, warped, not in some soft rubbery way you can touch, in a precise mathematical way that has nothing to do with any substance. Now imagine that mass, and also energy, because mass and energy are the same currency, mass and energy actually bend the space and time around them. A big heavy thing, like the sun, warps the space and time in its neighborhood. A smaller thing, like the earth, warps it less. A pebble warps it a tiny bit. Everything with mass or energy warps it some. Here is the punchline. Objects that are not being pushed or pulled by any ordinary force travel along what we call the straightest possible path they can, given the shape of the space and time they are in. In flat, unwarped space-time, that straightest path is what you would call a straight line. Ruler straight. But in warped space-time, the straightest possible path can look, to our eyes, like a curve. An orbit is the straightest possible line the Earth can travel along, given how warped space-time is around the sun. The apple that falls from the tree is not being pulled. It is following the straightest path it can follow, given that the Earth has bent the space-time around the tree, and that path leads, rapidly, to the ground. The moon is not held in its orbit by a rope. In a deep sense, the moon is coasting in a straight line. The line is just curved, because the Earth has bent the local space-time. Let me help you picture this. Imagine an airplane flying from New York to Tokyo. If you look at the flight path on a flat map, the plane seems to take this weird curve up over the Arctic, instead of going straight across. On a flat map, it looks like the plane is being pushed northward by some force. But of course, there is no force. The plane is flying in the straightest possible line. The Earth is round, and on a round surface, the straightest path between 2 points curves up over the pole. The flat map is a lie. The curve is the straight line, and the straight line on the map is the longer, lazier path. That is what is happening to the moon. The moon is flying in the straightest possible line. The flat map version of Newton says there must be a force pulling it sideways. But spacetime is not flat. The moon is taking the natural, straightest route available. The route just happens to close into a circle because of how the Earth's mass has curved the local shape of spacetime. If you find this hard to believe, good. It took the human race thousands of years to even imagine that space and time could be part of the action, rather than an empty arena in which the action happens. You are not supposed to find this obvious. You are supposed to find it bizarre. Now let me tell you the part almost nobody tells you. The part the pop science pictures always miss. Because when people explain curved spacetime, they show you a bowling ball on a rubber sheet and marbles rolling around in the dip. It is a cute picture. It is mostly misleading. Most of gravity for everyday objects is not from bent space. Most of gravity is from bent time. Let me say that again. The gravity you feel right now pressing you into your seat is mostly because time itself runs at different rates at different heights. That probably sounds like nonsense. Let me show you why it is true. Einstein's theory, when you work it out, says that time runs slower in the presence of mass. Time at the bottom of a staircase runs slightly slower than time at the top. Time at sea level runs slightly slower than time on a mountain. Time near the sun runs slower than time far from the sun. These differences are minuscule in ordinary situations, parts in a billion, but they are real, and they have been measured. People took two extremely accurate atomic clocks, synchronized them, and put one on an airplane, flew it around the world at high altitude, brought it back. The clocks no longer agreed. The flying clock had ticked a slightly different number of ticks than the one that stayed on the ground. The difference matched Einstein's prediction to excellent precision. So time near a heavy thing runs slower. Fine. Why should that cause anything to fall? Think of it this way. Everything is always moving through time. Even when you are sitting perfectly still, you are moving through time at the rate of 1 second per second. You cannot stop. You cannot pause. You are carried forward whether you like it or not. Now here is the trick. When time runs at different rates at different heights, an object at rest in space has a problem. Imagine a pencil sitting on a table, not rolling, not moving, at rest as far as the room is concerned. But the pencil is a physical object with a top and a bottom. The top of the pencil is slightly further from the Earth's center, so time at the top runs slightly faster than time at the bottom. The top end is, in effect, racing into the future a shade faster than the bottom end. When you work out, in Einstein's mathematics, what that means for the pencil's path through space-time, it turns out the pencil's path bends downward, curves toward the Earth, not because anything is pulling, because the pencil, trying to move through time in the straightest possible way, finds that the straightest way has a bend in it, and the bend points down. Here is an image that might help. Imagine two people marching side by side, arm in arm. They are walking forward at the same speed. Suddenly, the person on the left starts taking slightly smaller steps, while the person on the right keeps going at full pace. What happens? The two of them slowly curve to the left. The right-hand walker, still going fast, swings around the slower one. They were walking straight, both of them, but because their speeds differed, their path together curved. That is, at the deepest level, what gravity is doing. Every object has, in effect, a top and a bottom, a near side and a far side to every source of gravity. The side closer to mass moves through time a touch slower. The side further away moves through time a touch faster. And the object, keeping itself together, curves toward the slower time side, toward the mass, toward what we call down. It is not a pull. It is a natural consequence of trying to move through a region where time is not uniform. This is what Newton's apple is really doing. It is not being yanked. It is following the straightest possible route through a region where time runs a bit slower at the ground and a bit faster up at the branch. And the straightest route, under those conditions, curves downward. If you are a suspicious person, and I hope you are, at this point you should be saying, Feynman, this is poetic, but how do we know it is true? How do we know it is not just a different mathematical story that happens to give the same predictions as Newton? Let me give you the most practical answer imaginable. You know those satellites that orbit the Earth and help people figure out where they are on the surface? They determine position by measuring how long radio signals take to travel from the satellites down to a receiver. These satellites orbit at an altitude of about 20,000 kilometers, moving very fast. They carry atomic clocks on board because the whole position trick depends on precise timing. Here is the problem. Because the satellites are up high, where the Earth's gravity is weaker, their clocks run faster than clocks on the ground, by about 45 microseconds per day. That is from the time running slower near mass effect. Because the satellites are also moving very fast, a separate effect from special relativity makes their clocks run slower by about 7 microseconds per day. Add it all up, and satellite clocks run about 38 microseconds per day faster than ground clocks. 38 microseconds per day sounds like nothing, but light is fast. 38 microseconds of timing error corresponds to about 10 kilometers of position error every day. If the engineers building these satellites had ignored Einstein and trusted Newton, the whole positioning system would drift into uselessness within hours. A ship navigating by it would be placed 10 kilometers from its real location after 1 day, 100 kilometers off after 10 days. So what do the engineers do? They program the satellite clocks to run deliberately slower before launch, by exactly the amount needed to cancel the gravitational and velocity effects they know will happen in orbit. They are literally correcting every day in every satellite for Einstein's prediction that time bends near a planet. And the system works. Every time a ship, a plane, or a car uses a satellite positioning system to find its way, it is, in effect, confirming Einstein's picture of gravity. Newton's law, used alone, would fail. It is not that Newton is never good enough. For most engineering, Newton is spectacular. But he is literally not precise enough to run a satellite navigation system. Einstein's geometry is. So when I tell you gravity is not a force, I am not speaking metaphorically. I am describing the physics that runs the tools people use to find their way across the ocean. Once you accept this picture, all sorts of funny things fall into place. And other funny things become even funnier. Here is one. When you stand on the floor right now, you are accelerating. Not moving, accelerating. Your body, at this very moment, is being accelerated upward by the floor at about 9.8 meters per second squared. That is what you feel as weight. Your body would, if left alone, follow the straightest path through spacetime, which is the path of free fall. The floor is in the way. The floor shoves you. That shove is the only real force acting on you. Everything you call weight is the floor. If you jump, for a brief moment you are in free fall. No force is acting on you. You are following a straight line through bent spacetime. You are, for that fraction of a second, as free as an astronaut drifting in deep space. Then the ground arrives and punches you in the feet. That punch is what we call landing. Here is another. Astronauts in orbit around the Earth are not floating because there is no gravity up there. There is plenty of gravity up there. They are floating because they are falling. They are falling around the Earth, moving sideways fast enough that they keep missing it. Their free-fall state makes them weightless, exactly like Einstein's painter off the roof, but extended indefinitely. If you could magically cut off gravity, the astronauts would not start floating. They would start drifting off in a straight line into the distance, because the curvature that was holding them in orbit would vanish. Here is a third. Black holes. A black hole is a region where the warping of spacetime has become so extreme that even the straightest possible path, once you get close enough, bends inward. Light itself, trying to travel in its best attempt at a straight line, gets turned toward the center. Not because some gigantic force grabs it, because the very shape of the space and time near the hole has been bent so severely that every direction inside a certain radius points into the hole. Outward ceases to exist. That is what the famous event horizon is. It is not a wall. It is the place where straight lines run out of outward. Here is a fourth. Gravitational waves. If space-time itself can be bent, it can also ripple. Take two heavy objects and swing them around each other, and they disturb the space-time around them, and those disturbances spread outward as waves. Real waves. Waves in the shape of space and time itself, traveling at the speed of light. None of this is possible in Newton's picture. Newton has a static, unchanging backdrop on which forces act. In Einstein's picture, the backdrop is the main character. The backdrop does all the interesting things. Newton's force of gravity is not just wrong about what gravity is. It is missing almost everything interesting about the universe at large scales. So let me come back to where we started. To the apple. To the moon. For 2.5 centuries, we said the Earth reaches up through empty space with an invisible hand and pulls the apple down. We said the sun reaches across 150 million kilometers with an invisible hand and keeps the Earth in orbit. We drew diagrams with arrows. We called it the force of gravity. We built ships and rockets on it. We put men on the moon with it, because for those purposes it is close enough. But it is not what is happening. The Earth is not reaching. The sun is not reaching. There is nothing reaching. There is no hand, no rope, no field stretching out to grab. The Earth's mass has bent the shape of space and time in its neighborhood. The apple, when it comes loose from the tree, begins to follow the straightest possible path through that bent space-time. That path, because of the way mass bends time, leads the apple to accelerate toward the ground. The apple is not being pulled. The apple is coasting. We are the ones being shoved. By the tree until it lets go. By the ground after the apple lands. The moon is coasting too, in a huge, slow, elegant straight line that, because the Earth has bent the local space-time, loops back on itself over and over, year after year, century after century. Light, with no mass in the old sense, still bends around the sun, because light is also trying to travel in the straightest line it can, and when space-time is curved, even a straight line has a curve in it. If I have done my job, something in you should be stirring uncomfortably, because you have lived your whole life with a picture of gravity as a force, a pull, something reaching up from the Earth to grab you. And I have just quietly removed that picture. The floor you are standing on right now is not holding you up against a downward pull. The floor is shoving you upward, and that shove is every sensation of weight you have ever felt. You are not, in the deepest physical sense, at rest. You are being accelerated, always. As long as you are standing, sitting, lying on anything solid, you are being accelerated. The only way to truly rest, in the Einsteinian sense, is to fall. This is not a metaphor. This is the actual physics. There is one more thing I have to be honest with you about, because we do not yet know the answer. We understand in beautiful detail how mass and energy bend space-time. We understand how objects move through bent space-time. The equations work to astonishing precision. Every test we have thrown at Einstein's theory, it has passed. And yet we do not understand how the other forces of nature, electricity, magnetism, the forces inside the atomic nucleus, fit into this picture. Those forces still look, at the deepest level, like Newtonian-style pushes and pulls, with little carrier particles zipping between objects. Gravity, in the Einstein picture, is not like that. Gravity is geometry. The others are not geometry as far as we can tell. So we sit here with two possibilities. Either the other forces are secretly geometric too, and we have not yet seen it, or gravity is the odd one out, and nature uses two fundamentally different kinds of language to run its business. Either answer, if we ever find it, would change physics again. We live in a universe that is stranger than our parents' universe was. Space bends, time slows, light curves. The thing we used to call a force turns out to be the shape of the world itself. Newton gave us an extraordinary map. Einstein showed us that the map was drawn on paper that was itself bending. Somewhere beyond Einstein, waiting for somebody to find it, there is probably a deeper picture still, in which even the bending gets explained. I would very much like to know what that picture is. So I will leave you with this. If gravity is not a force, but the shape of space-time, then what do you think a force actually is? What, in your opinion, separates the real forces from this geometric business that only looks like a force? Tell me your guess, because the person who finally figures that out may well change physics forever.